All right, up until this point, we haven't actually mentioned this word geometric mean, this whole concept. So let's take a look. The geometric mean of two positive numbers, a and b, is the positive number x that satisfies this proportion. I've got a over x is equal to x over b. X is the number that we're looking for, which is supposed to be the geometric mean between a and b. It's a proportion, so I cross multiply that thing, right? So along one diagonal, x squared is equal to a times b. So if I were going to solve that quadratic equation, I would take the square root of both sides, and I would have x is equal to the square root of ab. Now technically you would have positive and negative square root of a times b, but in this geometric sense, we only ever talk about the positive one. Okay, so let me associate this with average, the arithmetic mean, where if we have two numbers, we want to find the average, we add those two together, and then we divide it by 2. So this is the geometric version of this thing, where we multiply our two numbers, and then we take the square root of them. So let's do an example, so we can see how this particular definition gives us the geometric mean between two numbers, and in this case, we're finding the geometric mean between 12 and 27. All right, find the geometric mean of 12 and 27, and I'm going to start this by writing myself a proportion. I'll start with the first one. 12 over x is equal to that same number x over 27. And again, whenever I go to solve this, the x number, whatever this x number is, that's the geometric mean between 12 and 27. So I'm going to cross multiply here, and I get x squared is equal to, and then on our other cross product, I get 12 times 27. Just maybe I need myself a calculator here. Let's calculate this. 12 times 27 is 324, of course. X squared is equal to 324. And just like the Pythagorean theorem, I have like x squared is equal to something. So I take the square root of both sides and get x is equal to the square root of 324. Believe it or not, it's 18. So what we just found here is the geometric mean of 12 and 27. And notice, of course, that 18 is someplace between 12 and 27. Well, let's just go ahead and compare this to average, like the arithmetic mean between those two things, so you can see how these kind of things compare. So over here on the side, let's find the average between those two numbers. So average, I'm supposed to add them together. I'd have 12 plus 27. I'd divide it by 2. Let's see, that's 20, 30, 39, which I think is 19.5. All right, it's in between there. As a matter of fact, when you have two numbers, it's like exactly in the middle between those two numbers. Let's just say, just for visual reasons, I'll put all of these things on a number line here. Make sure it's long enough. And let's maybe count by, I don't want to count by ones, let's count by twos. So 2, and 4, and 6, and 8, 10, 12. I'll label that one as a 12. Look how perfectly spaced these things are. 14, 16, 18, 20, 22, 24, and 6, 8. There's 28. I don't need to go much further than that. Oh, looks like I made mine a little bit too long. All right, so we have a dot here at 12, and then one at 27. And I'm going to put 2 other dots on here. One of them for the geometric mean, which is going to be in green, and it's supposed to be at 18. So 2, 4, 6, 8, right there. So 18, that is the geometric mean. All right, and then perhaps in, why not purple? In purple, we'll put 19.5. So we have 18. To the right of that is 20. Right in the middle would be 19. And so it's like 3/4 of the way there. and we have a 19.5 for the average or arithmetic mean, just so you can get a visualization of how these things all line up. Now, speaking of average, like we have a pretty good grasp of what we use average for, but like what do we use the geometric mean for? That's a fine question. Let's see if we can find out. Everything's got to restart. What the heck? Okay. So on example 4, let's find the value of x. And notice that in this picture, x is the length of the altitude in this right triangle, the one that goes from the right angle to the hypotenuse, and it's going to break up the hypotenuse into 2 parts. One of those parts, boop, is 12, and the other one is 27. Okay, so as I did in another video, I'm going to redraw some of these triangles so it makes it easier for us to set up a proportion. And this one in particular, if I take this small triangle here, I'm not going to compare it to the large one. Instead, I'm going to control it. Control it? How about compare it to the medium-sized one, right? Because as you'll see, the pieces that I have will match up. I'm not going to compare it to the larger one because on the larger one, I don't have the 2 leg lengths, question mark and question mark. But on the small one and the medium-sized one, those are the 2 pieces that I actually do have. So those are the 2 that I'm going to compare. And let's just redraw it so that it's easy to match things up. And when I do, remember to exaggerate so you have a long side and a short side. And then here's the right angle. Now, on the small right triangle, the shorter side is this 12 length that's on the bottom. So I'm going to put it over here on the left, 12. And then the x is on the longer of the 2 legs, not the hypotenuse because it's blank. So x. And now I should be able to set up my proportion. And it'll go like this. The 12 right there is going to match up with this x on the medium-sized one. And that should be equal to, this x should match up with the 27, the 2 longer legs here. X over 27, wait a minute, that looks familiar. I've already solved this proportion. I solved it right up here, didn't I? 12 over x equals x over 27. That's exactly what I get. And I already saw that that's equal to 18. And it's significant because that's the geometric mean. That's crazy. In other words, the altitude drawn from the right angle to the hypotenuse is the geometric mean between the 2 lengths of the hypotenuse it breaks it up into. In this case, our 12 and our 27 over here. That sounds like a theorem to me. Let's write it down, huh? So the altitude to the hypotenuse divides the hypotenuse into 2 segments. What is the relationship between the altitude, this x that's right here, and these 2 segments? Well, as we just saw on that previous example, it is the geometric mean between those 2 pieces. And we're going to call this the geometric mean theorem 1, or the geometric mean altitude theorem. So for your notes, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The length of the altitude is the geometric mean of the lengths of those 2 segments. All right, so whenever you're using this particular theorem to solve for a length, you could redraw the triangles like I did. It's not that tough. But when you have this configuration of pieces, I'm going to show you a little shortcut that'll help you set up that proportion without redrawing anything. And I call this the heartbeat method. So in order to understand this heartbeat method, I'm always going to start on the hypotenuse. And you can see, wait, let me back this thing up. Let me back it up. I'm going to start on the hypotenuse and think of, like on a heartbeat monitor, what a heartbeat would look like. Okay, so follow me here. So heartbeat method, I'm going to start at A, go up over x is equal to x over b. And then we flatline there. And whoever it is dead there. All right, so you can see that it makes it a very, very easy thing to set up our proportion. Let's take a look at this particular one on the one that we just did, this heartbeat method. So let's come back over here. And maybe switch this color to, I don't know, maybe purple. And you will see that when I start along the hypotenuse here, I'm going to start 12 over x is equal to x over 27. And that's exactly what I had in this proportion right here. Now, I could have gone the opposite direction. I could start at 27 and go in the opposite direction. I could go 27 over x is equal to x over 12, and it would not be exactly the same as this one, but it would solve the same way. It would just be upside down. It'd be the reciprocal, but x value would still be the same. All right, let's go back to the previous one that we did, which is over here, and let's see, could we have done the heartbeat method on it? Let's take a look, huh? Maybe in green this time. It would be, I don't know, blank over x is equal to x over other blank. No, it doesn't look like the heartbeat method works on this particular one. It's not going to work every single time, but when you have this set of pieces for that particular theorem, and that was the altitude theorem, then it does work. In order for the heartbeat method to work on this one, we would have to know what these two pieces are, and we just weren't given those two pieces for this particular example. Speaking of examples here, let's try one more. Example 6. Find the value of w. And notice that in this particular picture, in this right triangle, w is part of this expression which gives us the length of the altitude. The altitude is breaking up the hypotenuse into two pieces. This w plus 9 should be the geometric mean between these two pieces, 8 and 18. This looks like it's set up to be a heartbeat. Let me scroll down, go all the way down to that example. Whoa, that's too far. Here we go. So I set up my little heartbeat, and it's going to look like this. 8 over w plus 9 is equal to, why did you just do that? 8 over w plus 9 is equal to w plus 9 over 18. And let's set it up and solve it. 8 over w plus 9 is equal to w plus 9 over 18. Now we have our proportion. We're just going to solve this thing for w by doing some cross multiplication. So our first cross product here would be w plus 9 times w plus 9, and I'm going to suggest that you just write that as w plus 9 squared and do not FOIL it out, is equal to our other cross product here, 8 times 18, go away. 8 times 18, that would be 80 plus 64, 80 and 60, whoops, that's not 64, which is 114. 144. 144, yeah. And I didn't want to FOIL that thing out, because just think of this thing as like an x squared is equal to 144, right? And then I could very easily just take the square root of both sides and get rid of that square that's on the left-hand side. So I'm going to take the square root of both sides. Bojoop and bojoop. All right, on the left-hand side, I get w plus 9, because the square and the square root are going to cancel out. Now, technically, it's actually the absolute value of w plus 9, but we don't have to worry about that. All of our lengths are always going to be positive, so that's good to go. So we get is equal to 12 on this side, and then finally just subtract our 9 over, and we get w is equal to 3. Boop, boop, boop. All right, so that concludes example 6. But the geometric mean has another application to right triangles, which we're going to see